Alright guys, so today we're going to be drawing advanced Lewis structures, specifically polyatomic ions. And polyatomic ions, for example, are sulfite, phosphate, and carbonate. Sulfite is SO3 2 minus, phosphate is PO4 3 minus, and carbonate is CO3 2 minus. So these polyatomic ions are always together. As you see, they have multiple components, but they're covalently bonded. So let's start with sulfate. So for sulfate, you have SO3 2 minus. You have that 2 minus charge right here, and sulfur has 6 valence electrons, and oxygen in this case has 6, but there's 3 oxygens, so that's going to be 18 valence electrons. But don't forget about the 2 minus charge. From here, we can acknowledge that sulfur is the central atom since there's 3 oxygens and only 1 sulfur. So sulfur would be in the middle in this case. I like to draw it in a line model instead of the dot model. You have 3 oxygens that are bonded to the sulfur, and since sulfur has 6 valence electrons, it only has 3 bonds here, and sulfur is giving away sharing 1 electron, sharing another electron to bond and sharing another electron to bond. That's going to be 3 electrons only, so we're going to have to put 3 more right here to have 6 valence electrons. Oxygen, on the other hand, has 18. However, it's also sharing 1 right here, so it's going to have 5 at first. But still 6 in total. But because of this 2 minus charge right here, the minus means the addition of electrons. So we're going to have to add 2 electrons to 2 of these, or 1 electron to each of these oxygens, except this oxygen will not get that another electron because it's only 2. So we can only disperse it to 2 oxygens. So I'll give this oxygen 1 electron right here, and this oxygen another electron. However, this oxygen doesn't get it because it's only 2 minus. If it was 3 minus, on the other hand, it could have gotten, or it would have gotten the electron. So these oxygens are good to go, but this oxygen right here is very unstable right now. It only has this 1 little lonely electron right here, and it has another, and this sulfur has a lonely electron right there. So when 2 of these electrons are lonely, they often meet together to create a double bond, which I'm going to draw right now. So this sulfite is going to become this, still the oxygens, normal oxygens, and the addition of that electron on 2 of those oxygens. But over here, we're going to have a double bond over here, because these 2 electrons are now added to make a double bond. So when these 2 electrons are added into the double bond, we're only going to have 4 electrons on this side. So we just draw 4. And now, in order to understand if our model is proper, what we can do is we can calculate sulfur's bonds and valence electrons combined. I forgot to add those 2 valence electrons right there, because these 2 valence electrons, nothing happens to them. So in this case, sulfur has currently 2 valence electrons on the outside, and it has 1, 2, 3, 4 bonds. So 2 plus 6, or 2 plus 4, I apologize, equals 6. Then we have 2 different oxygens here. We have oxygen A, these 2 are the same, and we have oxygen B. This one's different than the other oxygens. So for oxygen A, we have 1, 2, 3, 4, 5, 6, 7. So we have 6 valence electrons plus 1 bond. That equals 7. For oxygen B, on the other hand, we have 1, 2, 3, 4, 5, 6. So it's going to be 4 valence electrons and 2 bonds, which equals the 6 I counted. So these should show you that this sulfur has a 0 charge and this oxygen has a 0 charge, while this oxygen has an extra electron, so it's going to be a -1 charge. However, since there's 2 of those, you just multiply that by 2. There's 2 oxygen A's. And that's exactly what gives the sulfite ion that -2 charge. So if we draw that again, we can draw the bracket and put a 2 minus. Make sure you always remember this bracket. It's very important. Now in terms of resonance structures. So resonance structures say that certain molecules, we can move the bonds throughout the atom or the molecule or structure, and it will still stay the same. So in that case, to draw these resonance structures, we can understand that this double bonded oxygen to the sulfur can go here too, and can go here too. Since there's 3 oxygens, they're all the same type. To draw a resonance structure, we can draw our normal Lewis structure for now with the lines. Don't draw the valence electrons just yet. However, we must show that there can be double bonds for each. So how we do that is we add a dashed line. And when we add a dashed line, we have to show the potential of the valence electrons. Since oxygen A is different than oxygen B, we must show that the potential is oxygen B. So we only draw 4 valence electrons around each oxygen in this case. And that's our resonance hybrid. For phosphate, on the other hand, we have PO4 3-. We know that phosphorus has 5 valence electrons, and oxygen has 6 valence electrons times 4, which is 24, because of the 4 oxygens. And we can tell that this has a 3- charge. So when we draw our central atom of phosphorus and draw each oxygen bonded to that phosphorus, we must also add 1 electron to 3 of the oxygens. Not 4, because it's only a 3- charge. So in this case, this would be 5, but since it has a 3- charge, we add 1 here. Same with this one, and same with this one. This oxygen, on the other hand, does not have that potential because it's only a PO4 3-. But this phosphorus, we forgot that 1 valence electron that's left out because it only is sharing 4 electrons right now, so it must have 1 over here. So this 1 valence electron can, once again, jump there, and this lonely valence electron can jump there, creating a double bond. So this phosphate ion is going to be like this. And it's going to have a double bond right here with 4 electrons over here, 6 over here to complete its octet, and 6 right here. And of course we have to add the 3- charge. And in this case, if we calculate this once again, we have oxygen A. We can name these oxygen A. We have 3 of those. And they're going to have 6 electrons on the outside and 1 bond, which equals 7. Oxygen B, on the other hand, is going to have 1, 2, 3, 4, 5, 6. So it's going to have 4 electrons on the outside, and we're going to add 2 bonds, which makes it 6. And this phosphorus is going to have 1, 2, 3, 4, 5 bonds. So this phosphorus will have just 5 bonds. So for our oxygen B, it looks good. It has a 0 charge. This has a 0 charge because it fulfills the valence electron rule. Oxygen A, on the other hand, has 1 extra electron, so it must equal a -1 charge. However, there are 3 oxygen A's in this case, so we multiply by 3, which makes a -3 charge. So this fulfills what we wanted. In terms of resonance hybrid, we have a phosphate right here, and once again we can draw the 4 lines. Start it off simple. Draw our oxygens. And since we have a single bond right here, a double bond right here, the double bond can move throughout the oxygens because these are all oxygens. But remember, it must retain the potential number of electrons on the outside. So all oxygen in this case must have 4 electrons on the outside. And with the bonds, we can show a double bond with the dashed line. And once again, we must draw our bracket showing a 3- charge. And that shows our phosphate. Lastly, we can do carbonate, which is CO3 2-. Carbon has 4 valence electrons. Oxygen has 6 valence electrons. 6 times 3, which is 18. And remember, this has a 2- charge. And we know in this case that our carbon is the central atom. And carbon is usually a central atom because it has the capability to bond to 4 things. But this oxygen can go right here, this oxygen can go right there, and that oxygen can go right there. But carbon in that case has 1 extra valence electron right here. Oxygen has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. But we have to take account of the 2- charge, so we must add 1 electron here and 1 electron here. This carbon with this lonely electron and this oxygen with this lonely electron can meet at this bond and create a double bond. So that double bond is created. And in order to calculate the charges, we'll do this. For carbon has 0 extra electrons. It has 1, 2, 3, 4 bonds. So 4 plus 0. And carbon has 4 valence electrons, so the charge must be 0. And in this case, once again, there's 2 different types of oxygens. This is oxygen B, we can name it, and this is oxygen A. Oxygen A, in this case, will have 6 plus 1, which equals 7. Oxygen B, in this case, will have 6. 4 plus 2. I apologize. 4 plus 2, which equals 6. So this adds up to oxygen's valence electron rule. This adds up to carbon's, but this is 1 extra, so it's going to be -1 charge, but there's 3 oxygen A's, so you multiply it by 3, and you get a -3 charge. Sorry, not -3, 2, and then you get a -2 charge. I apologize. So we can finally add that bracket right here saying 2-. And going back to resonance structures, you can do the same thing in terms of carbon having these 3 oxygen bonds and having dashed lines for both, or all, but it's only having 4 here and 4 here. And then we add the bracket for the 2 minus. And that is our resonance structure. And that's going to conclude the video for today on polyatomic ions and Lewis structures.